So what I'll do next is get into the climate projections uncertainty a little bit and talk about where it's coming from. So, and before I do that, I just want to talk a little bit about climate variability. And I think Katrin touched on it a little bit, but you know, this term variability is, as opposed to climate change, is just fluctuations, the up and down around a long-term climate mean. This fluctuation in climatic conditions on timescales of months, years, decades, centuries, and beyond that. So we live in a dynamic system. And chaos is part of its nature. Stochasticity, as we say, is central to our climate system, because we have atmosphere and ocean, and there are flows, and there are all these stochastic or randomness to our climate system. And part of that produces this variability. So multiple set of drivers, internal and external, working to produce fluctuation, if you will, in our climate expression, or the climate expression of our planet. And that has global and regional effects. So what you see here in the graph, I put just a very few examples of like how you can visualize variability, but up above is just the expression of sea surface temperature in the Pacific through the El Nino Southern Oscillation Index. So it's a very large area, expression of a very large tropical Pacific area. And it's just saying how the temperature of the sea surface varies, and that has real, regional to global implication. And I'm just showing below just a regional temperature, regional precipitation, and that's here for Northern Great Plains, where you see, times of high precipitation to, very big drought years. This is the 30s drought year where my pointer is pointing, which is one of the driest part in our observed record. The 30s, that coincided with the Dust Bowl era. And so variability really drive, the climate and weather extreme we see, and especially historically, they were the big drivers, the long-term persistent extremes to even short-term droughts that could just emerge. So like this is the 2012 drought, I believe. Again, a severe drought that emerged in what was a very wet, a long-term wet period in the Northern Great Plains. So as the climate is changing in a certain directional way, so I'm showing this graphic of temperature anomaly, and this is global temperature. But you see around that there is fluctuation. So we need to account for, so as the climate is changing, the climate is still doing its thing of being variable from year to year, from decade to decade. And it will bring warmth or coolness at times, or more moisture versus less moisture, and that would drive expression of climate for that period, and which would be expressed as both droughts or floods. But the point I want to make here is they add to the uncertainty. As you can see that, we talk about stakeholders in the Northern Plains already dealing with this high variability in climate and adapting to that. And so one sense is if we are well adapted to the historical variability, does that also mean that we are adapted to we are better adapted to future climate change? And perhaps not, because we are probably moving out of the envelope of historical climate variability. Okay, so I wanted to make a point about variability before I show you this figure. And here I really want to get into the sources of uncertainty in future climate change or future climate projections. and really talk about these three sources. One is that just emerging from variability, just the randomness of the climate system, just the fluctuation. The other source is differences across models, difference across different climate models. And you sometimes see difference across the same climate model run multiple times. You would see differences. But this is really talking about intermodal differences. It's not talking about differences across the same model, because that difference is really controlled by variability. So this, when you look at differences, the blue, the differences across one GCM from one center versus a GCM from another modeling center. And the green is the difference that's emerging from which emissions pathways or scenarios we go on. So are we going on RCP 4.5 or 8.5? And what difference will that produce? So what this figure is about temperature, regional temperature, and what influenced the uncertainty in regional temperature projections. And if you look at these three criteria, we see that in the short term, a period of years to a decade, the internal variability plays a very big role. But beyond the 10-year mark or 20-year mark, it's the differences across the GCM, across the model, that play a very significant role. And only after like 2050 or so that the influence of emission scenarios start to play a bigger role. But even then, in the late century, both the difference across the models and the emission scenarios are important. Okay, so let's look at precipitation. I'll just say again, so differences across models play a very big role throughout the 21st century in influencing our uncertainty in temperature projections. And when you look at precipitation, it looks quite different from temperature. And where you see that the variability, the uncertainty in projection, future projection, just emerging from fluctuation, randomness, is very big for precipitation. So it influences several decades into the 21st century, and still is relevant. Explains 20% or so of the variation later in the 21st century. And again, I want to emphasize I'm just talking about regional expression of projections. This is not global. So it's really looking at regional. So variability is very big for precipitation, but also what's very big and continues to grow during the 21st century, later in the 21st century, is the difference across models. In some of the difference across models, there is, I believe, is some component of variability there. So for precipitation, the big message here is that the future emission scenarios play a very limited role for regional projections in affecting uncertainty across in future projections. It's really differences across the climate models and the variability that are the big factors. Okay, so let's look at the uncertainty emerging from emission scenarios and the intermodal differences a little more. And before I do that, I just want to touch a little bit on this emissions piece. And because there's always this question that I'm asked by practitioners: what should we choose? Should we work with RCP 4.5 versus 8.5? And next few years we'll be using the word SSPs. Should we work with SSP 4.5 or SSP 8.5 or others? And so several papers, that I'm just citing one here, that have come and talked about the likelihood of some of these pathways. And so often, sometimes used to call the RCP 8.5, which is very similar to SSP 8.5, so leading to this kind of future and emissions and future in terms of climate change as business as usual. But scientists have been arguing that please don't call this business as usual. Based on current policies, the pathways look somewhere in this direction, closer to RCP 6.0, somewhere between 6.0 and 4.5. So from just that perspective, the way the current policy is unfolding, the likelihood of these scenarios is greater. And these scenarios really should be thought of 8.5 as a worst case scenario, but with a very low likelihood. Yeah, that's all I'm going to say about likelihood, and that's it. So that doesn't mean that you do not work with 8.5, and you'll see a lot of papers and a lot of work includes 8.5 in their assessment. But when you work with something like an 8.5 scenario, emission scenario, the thinking there is you're working with the worst possible outcome in terms of climate change and impacts. So I just want to show you a few plots describing the influence of variability and emission scenario. The intermodal differences and emission scenario on future projections. So what you see here is for a Southwest Colorado region. I'm showing a time series, a smooth time series of annual mean temperature. And what you see in the red is RCP 8.5, and the blue is RCP 4.5. And the thick lines are the mean values, and the range or the cloud around these lines are the differences across the models. So you have the difference across the models shown through these, and then difference across the scenarios shown in these two colors, blue and red. And so what you start to see for temperature, again, at the regional scale, is that only after the mid-21st century that the emission scenarios start to show difference across the projections. But before that, it's really the differences across models. So next 20, 30 years out, it's really differences across these models that are causing much of the uncertainty. But if you're looking really at the end of century, the emission scenario uncertainty is pretty big, and is comparable to that of intermodal differences. So that's for temperature. If you look at precip, again, it looks very different. And again, I'll just not spend too much time here, but to show that the differences across the red and blue is hardly noticeable here. And much of the difference in future change in precip comes from differences across models. And variability is very much part of it. I'll show you the same information in slightly different ways, and I'm going to spend a little time on describing this graphic because we use quite a bit of these scatter plots to look at future changes in climate in a region, look at the spread in that, and also, as I say, select scenarios. So what you're seeing here is for the Southwest Colorado region, changes in annual temperature and precipitation from, about 35 different models that are run on the two different emission scenarios. So you're looking at change by 2035, which is a 30-year period centered on 2035 relative to the last 30 years of the 20th century. So what you see here is that these models suggest change in temperature from 1 to 3 degrees Celsius, and precipitation change anywhere from -10, decreases in 10% to increases in 10% precip, and anything in between, everything in between. So one thing you quickly notice is that the red and the blue dots really overlap each other. So there's very little difference between emission scenarios. So the 2035 centered on this period centered on 2035 actually goes all the way to 2050. So you're seeing a period from 2021 to 2050 here. As you move further along into mid to late century, what you start to see is that the red and the blue are now separating, particularly around the temperature axis, not so much around precipitation. So again, as I mentioned earlier, emission scenarios affect less of the precipitation change and really influence more of the temperature. And if you go later in the 21st century, you kind of see red and blue separate much more, but again, largely along the temperature axis. If you're really interested in this topic and see how we work with uncertainty, how our stakeholders are actually working with climate data and uncertainty and doing, so some of our stakeholders here, we have a session tomorrow morning, and this is a plug for that. In case you really want and you don't have the Zoom link for it, you can email me and I should be able to get you a link. So just I want to say two things here. We are working with a scenario-based approach with many of our stakeholders to kind of work with this uncertainty in climate projections. And one way it looks like is, I showed you a graphic similar to this earlier, working with the spread in the projection, in this case, working with this bivariate plot, but there could be other ways, more nuanced ways to work with the spread in projection and selecting scenarios. And so part of the process is selecting and working with specific future climate scenarios. And in this project with the Nature Conservancy, we work with 4 specific scenarios to look at climate change and impacts in Colorado. And just another plug, that Climate Toolbox is one tool that can really help you generate these kind of plots and do these kind of scenario selections. And with that, I'll just hand over to Catherine.